Okay, so today we're going to talk about acids and bases. This would be the second part of Unit 7, with the first part being solutions and colligative properties. Um, anyways, so acids acids and bases are separated into three different types based on how they interact with their surroundings and other chemicals. So, first thing we're going to ask is, what is an acid? And what is a base? So, the most general terms of both of these would be that an acid ranges from 0 to 7 on the pH scale. And a base ranges (7 to 14 on the pH scale. And just so you know, the pH scale is just a way for us to analyze the concentration of hydronium ions. So we have 7, put 0, 14. So your acids will be here. Let me fix this drawing a little bit. And then your bases will be over here. So this is more like just the general gee-whiz info about what an acid and a base is. So let's go over some definitions. So we have Arrhenius acids. Yeah, my pen died. So we have Arrhenius acids. So Arrhenius acids produce hydronium ions in solution. Hydronium. So hydronium, if you look at your polyatomic ion sheet that I put on Canvas in, I think, Unit 4, you'll see that you have H3O plus would be your hydronium, but oftentimes, to save some work, we just represent it as H plus. Because what hydronium actually is water with an extra H, making it have a positive charge. So, put a little arrow to link these two. Okay, so that would be your Arrhenius acids. They produce hydronium ions in solution, so H plus. So an example of this would be like hydrobromic acid, which would be HBr. So in water, the acid hydrobromic acid dissociates and then this means that it's forming H plus and Br negative. The H plus binds with the water forming hydronium. So the overall chemical reaction would be HBr, H plus plus Br negative. Okay, And then this would be like the shortened one. The actual one would be all right. H2O, just so you know, is often not written. It's just implied. See how much time. Okay, perfect. So, an example of a acid that would be used by your body is actually hydrochloric acid, which you probably heard of. So, your body naturally produces it. Your body naturally produces hydrochloric acid to break down food. Alright, so I've already gone over what an acid is and an Arrhenius acid. Just to recap, Arrhenius acids form H plus when they're in solution, or they form H3O plus. Either one I will accept. Just know that H plus means H3O. Excuse me. Alright, so an Arrhenius base is the opposite of this. An Arrhenius base dissociates in solution to form hydroxide. Or actually, not to form, just put forming hydroxide ions in solution. So a good example is one that I use a lot when we're talking chemical reactions. It's sodium hydroxide. It's a very strong base, and it's Arrhenius base because it forms hydroxide ions in solution. So this would be sodium hydroxide. In solution, let me put the little EX thing. So in solution, dissociates, forming Na plus and OH negative. Now I'm going to keep going on to the next page. So I'm going to copy this real quick. All right. If you need to go back and see everything, feel free. So anyways, in solution, sodium hydroxide dissociates, excuse me, forming sodium plus 1 and hydroxide ion. So this would be how you write it, would be NaOH. And then over here would be Na plus OH negative. So strong acids and strong bases. This is something you need to be aware of. So strong acids and bases dissociate, meaning they dissolve 100% in solution. Weak acids and bases so your weak acids and bases, if you can guess, dissociate less than 100% in solution. Okay. If you need to copy that, feel free. I don't know what's going on. Make sure it's still recording. Alright, cool. So, let's go to the next page of my notes. Alright, I think I got room here. Yeah. Let me go to a new page just in case. Doesn't really matter because these are already on Canvas. So, what I want you to do is copy this. And we're going to have 2 columns. So, let me fix that arrow. Okay, so we have strong and weak. So I'm going to write down some of the more common strong acids and some of the more common weak acids. So one thing you need to be aware of is strong acids are going to have an arrow like this. So it's always, you can represent an acid as HA. And then this arrow is for strong acids because it's going to completely dissociate. And then over here, you would have HA with an equilibrium arrow, meaning it can go back and forth because there's going to be a balance between the two. So let's write down some acids. You have hydrochloric acid, hydrobromic acid, hydroiodic acid, and then we have nitric acid, and we have sulfuric acid. So these are called your binary acids. And these are oxy acids. Now over here we have our weak acids. We have hydrofluoric acid, and then HNO2, H2SO3, and then we have some carboxylic acids, which are organic. So your organic acids are things like vinegar, like acetic acid, and I think this is formic acid, which is actually able to form formaldehyde. So you don't need to know the names of all these, just kind of gee whiz info for you. Kind of expect you to know these and these two, but these don't worry about. Alright, so this is the list I expect you to copy and understand. You have weak over here, strong over here. Alright. Bases. So, just like acids, we have strong and weak bases. Alright, so for a base, we put BOH is equal to B plus OH negative. And then over here, same thing, it's just going to have an equilibrium arrow. Alright, so usually these follow something simple. You're going to have a metal from group 1. And there's tons of different bases. I'm only showing you like some really common ones. So group 1 plus, close that off too early, plus hydroxide. And then over here, we have some organic compound with nitrogen. Oh wow, I screwed that up. Here we go. Let me move that over so I have room. Okay, so there's other acids you could have. That's lithium hydroxide. sodium hydroxide and potassium hydroxide. You can also have stuff like sodium amide. It's also a very strong base. Sodium hydride, very strong base. But anyways, these are like the common ones you're going to see is with hydroxide. You won't see these really unless you're doing like organic chemistry. And then over here, we're going to have ammonia and CH2 and H2. I don't even know what this is called, but anyways. That would be the general format for your acids and bases that are Arrhenius. Now, Arrhenius isn't the only type of acid and base that you can have. The next thing we're going to cover is our Bronsted-Lowry and Lewis definitions of acids and bases, because the Arrhenius definition is kind of limiting in that if you had a Venn diagram, you would have Bronsted-Lowry. I'm going to draw it in the next few seconds, or next few minutes, but Arrhenius only encompasses so many of acids and bases, but Bronsted-Lowry allows for more, and so does Lewis, that the Bronsted-Lowry doesn't cover. So I'm going to go to the next page, and we're going to go on. So this is still acids/bases, and we're now going to go over what the Arrhenius theory is. I guess I kind of covered that, but I'll give you like the verbatim definition. So an acid is a substance that can give away hydrogen when dissolved in water. I don't like the way that's worded. Give away hydrogen ion when dissolved in water. Alright, so there's more bases and acids that don't really fit into this theory. So we're going to go over the Bronsted-Lowry theory. So we're going to talk about what a Bronsted-Lowry acid is. It's any substance that can donate a proton. Okay, so let's go over this. When you look at a Bronsted-Lowry and it says a proton, many of you are just thinking P+. I'm going to give you a tip that nobody ever told me that made it easier for me to understand. If you look at hydrogen by itself, it has one electron, one proton. When you have something like HCl or CH3COO. Actually, let me rewrite that. That's terrible. CH3. So this H would be where it's coming off at. And then this one, you're actually donating, the electrons are not coming with the hydrogen. You're just giving away a proton, because even though this is missing its electron, which is what deviates the charges of elements, you're giving away a proton. So I'm going to give you an example. So we have acetic acid, and then this is in water. You're going to have acetate which is what is made. And if you look, this is for sure a polyatomic ion that I told you to memorize. C2H3O2 -1 plus hydronium, which is also one I told you to memorize. Anyways, right here, this is your acid, this is your base, this is your conjugate base, conjugate acid. So what that means is these can combine and go back to this way. Like this can go this way and this can go this way. That's what that equilibrium arrow is talking about. So I'm going to draw the Bronsted-Lowry base. Let me write Bronsted. Actually, it's there. We'll just write acid. We know that's what we're talking about. Bam. All right. So a Bronsted-Lowry base is different. Has nothing to do with hydroxide. And this is where the definition allows for more Bronsted-Lowry compounds than Arrhenius. So a Bronsted-Lowry base is a substance that can accept a proton. Okay, so an example of this. You have NH3, which is ammonia, plus H2O. And then we have our equilibrium arrow. And you have ammonium, which is polyatomic ion I told you to memorize, and hydroxide. So here is our base. This is our acid. It's our conjugate acid, conjugate base. So I'm going to go over those two, don't worry. So just so you know, this accepted a proton from water, which is why it is a base. Because it doesn't, on its own, it doesn't give away or produce hydroxide, but it accepted a proton. So let's kind of write these down. And then okay, proton donor. We're going to write down what a proton is and has a conjugate base. Okay, this is a proton acceptor, the Bronsted-Lowry base. So, has a conjugate acid. And you guys are probably wondering what these two words mean right here. So let's write those down as well. And I'm going to color code them so you know which one it goes with. Conjugate base. And then this one's going to have its conjugate acid. So our conjugate base is a base that forms when an acid loses a proton. Let me make some room here. Our conjugate acid is an acid that forms when a base gains a proton. So if you need to copy this, just pause it, copy it. I need to move to the next page. So let me draw a circle. And we're going to draw a little one inside after I write stuff. So in the little circle, we have our Arrhenius acid and base. Up here we have our Bronsted-Lowry. So what this means is Arrhenius acids and bases are also Bronsted-Lowry acids and bases. But that's not always the case vice versa, which is why there needed to be separate, distinctions between what makes an acid and base. And then last thing we're going to go over is the Lewis acid and base. So I'm going to use the same color scheme. So a Lewis acid, a substance that accepts an electron pair to form a covalent bond. And then a Lewis base is a substance that donates an electron pair to form a covalent bond. And then we have our Lewis acid-base reaction. So our Lewis acid-base reaction is a reaction in which a covalent bond forms between an electron pair, forms between an electron pair donor and acceptor. And that is it for this video. Make sure you brush up on these definitions because these are going to be important later on.